Hello, everyone. Today we have Daniel Tamayo Jimenez from the Université Paris-Saclay, who will talk about permutree sorting, pattern avoidance, and automata.
Thank you, Aram, and thanks for inviting me here. Thanks for the organizers. And yeah, I'm going to talk to you a bit about my work that has been going on as a PG student under Vincent Pilat and Vivian Pons here at Paris. And more than anything, based on a paper that we wrote some months ago called Permutree Sorting that's right now in the archive. And the outline of the structure of the talk that I'm going to give is the following. I'm going to start by giving some motivation about the problem. Why are we attacking it this way? Why automatas? Why are we doing this? Afterwards, I'm going to show you a little path of how do we, from the objects that we are interested in, end up dealing with automatas. After that, after the pause, actually, I'll go into the main part of the talk about the algorithms that we define with our automatas and how they allow us to characterize certain combinatorial properties of permutations. And lastly, I'll close up by showing you the relationship between our permutree sorting with other notions of sorting known, and in particular, C-sorting or Coxeter sorting. And perhaps if TEMS allows, I'll tell you a bit about how this leads or how this connects with the same ideas on other Coxeter groups. So to start, why automata? Why do we bring automatas to the table? Well, first of all, we'll be dealing with lattice congruences of the weak order. And these are congruences that have been already studied a lot by Nathan Reading in several articles, actually. Like, he has a total of four and maybe a bit more articles that deal with these types of lattice congruences. But as is commonly known with Coxeter groups, these types of problems can be attacked through several perspectives. And those include, but are not limited to, lattice congruences themselves, root systems, reduced words, and pattern avoidance in certain finite types, like types A, B, and D. And well, I'm going to tell you more about later what are we doing exactly, but some of these perspectives are really computationally hard to check, or the intuition is not really that easy in some of them. So we needed to find another perspective that actually encodes the same properties, but that's kind of more tangible for what we want. And well, since we have reduced words and automatas are something that are linked to words and reading words and codifying some characteristics of those words and those languages. Vivian Pons actually was the one who brought this idea and said, oh, maybe we can do something using automatas. And basically, that was it. We just wanted to codify our problem in another way that's more useful to us. So the big objective that we have actually is the following: that if we take the weak order of permutations, and in this talk, I'm just going to center myself around permutations and type A, that is the type A Coxeter group, the Coxeter group of type A. And if we take lattice congruences of the weak order, we would like to characterize the minimal elements of the conjugacy classes that we get. So if we have lattice congruences, that gives you congruence classes. And the special thing about these congruence classes in the weak order is that they always have a minimal element. And we would like to characterize them in general. and depending on which lattice congruence you get, the structure will differ. And these are what permutrees are defined as. I'm not going to go deep into what permutrees are. That's a whole other conversation, but that's basically from where the title comes up of permutree sorting. So permutrees, for the sake of this talk, is just the minimal element of these congruence classes. And there are always other characterizations that have been found in different papers, in different works. For example, the one in 2018 by Pilot Pons, and in 2019 of both of them with Gregory Chartel. And these characterizations are based around pattern avoidance, the minimality of linear extensions of permutrees themselves, and characterizations in inversion sets. So, but the thing is that these characterizations are all in type A and not in the general case. So in contrast to Ryu's work, this is just limited to type A. And the idea is also to generalize this to other types and see what works in other types. So now that you know what permutrees are, let me tell you about what sorting is. So sorting is just basically any algorithm that rearranges a permutation. So you just have an algorithm, you feed it a permutation, and it spews out another permutation. And depending on if the output is the identity permutation or not, we say that a permutation is sortable for a certain algorithm. So, well, what's the classic example of this? Well, it was first defined in the 60s by Knuth, and it's called the stack sorting. And what this algorithm does is that it takes a permutation on n objects, and it just throws you a permutation where you take the biggest element, the biggest number, and you place it at the end. So you just take an S of tau n rho is just S of tau, S of rho, n. So in general, these algorithms, not necessarily, but in general, are found in this sort of recursive fashion. And if we go on and do this, for example, this stack sorting algorithm for all the permutations of length 3, we find out that most of them give us the identity permutation. That is, most of them are sortable for the stack sorting algorithm, except for one of them, which is 231. And if you stack sort it, you find out that the permutation at the end of the algorithm is 213. So this seems very trivial in n equals to 3, but when you go on to higher dimensions, we find out another phenomena, that is that the collections of permutations that all get stack sorted to the same element are an interval, and that's basically the interval that we are interested in. So for example, in this case, well, except for the minimal, which is, since it's stack sortable, it's the identity. So the interval in this case would be 213 and 231. Everything that's in red and 213, that's the interval that we get in this case. And the other conjugacy classes are only the elements by themselves. So this actually is linked. The stack sortable permutations are in bijection with binary trees, which are in bijection with permutations that avoid a certain pattern. And this is one of the other perspectives in which all of this, in which these ideas start to mix up. So, as I said before, we are interested in permutations. That will be our main object of study. And we are really interested in working with a specific presentation of the permutations. So the symmetric group, and that is just its formulation via the braid relationships. That is, I have n-1 generators, where Si is just a simple transposition I with I plus 1, and the relations Si and the braid relations that you can see here, and these that are generally well known. So with that, here's an example of how the weak order on permutations looks like. So I'm just going to say it for completion sake. The weak order, the way that I define it, is this is the right weak order, and that is I take a permutation and I multiply it by the right by a permutation, and that transposes two consecutive elements. And this is the resulting poset that is actually a lattice. And here I codified, or well, I colored the edges between the edges of the whole poset with respectively following which reflection, which transposition they correspond to. So say if I want to go between the permutation 3, 1, 2, 4 to 3, 1, 4, 2, I go with a transposition S3 that is changing the third and the last position, and this will come into, this will be important later on because we are really interested in which transpositions lead one permutation to the other, and what does this cause with our sorting algorithms. So I've been talking about that we want to do congruences of the weak order, but we don't want to do any type of congruence because that's something that you can do in general. But we want to do something that's called basically a lattice congruence, and that is a congruence that preserves meets and joins of a given lattice. So in this case, we call them lattice congruences. And what that means is that, well, yeah, it preserves meets and joins. These are the equations that you see here. But how does this look like in the poset? Well, there are two particular cases that we will be interested in since we are working with a weak order of permutations. And if you study the weak order of permutations, you always see that the I don't want to say minimal cycles, if you see it as a graph, are always hexagons or squares. And if you work with this more in the geometrical point of view, these are just like facets of the permutahedron. They are always squares or hexagons. This comes from the braid relations. So we want to here look at what does this lattice congruence do to these hexagons and squares. So in the case of hexagons, what happens if I start by defining that my congruence class, that in my congruence class, there must be a class where B and D are in the same class. And that's represented here by the blue edge. So if you calculate any other meet and join between the elements A, B, C, D, and E and F, well, you see that everything holds, nothing else is affected. So if I contract this edge, if I contract the blue edge, nothing else is affected. All the other things remain the same. But instead, but in the opposite case, what happens if I contract the edge between A and B? Well, in this case, if I start calculating other meets and joins, like if I do the meet between E and B and E and A, well, B and A are in the same congruence class. So I need that these two meets are in the same congruence congruence class as well. And this just tells me, okay, the opposite edge should also be in the same congruence class. So F is in the same congruence class as E. If I do the same, if I do the join between C and B and C and A, I get that F is also in the same class as C and E. And the last one that we get is that the meet between D and F should be the same as the one between D and E. And that just gives me two congruence classes where I have three elements in each. So basically in my first case, my hexagon got collapsed into a pentagon, while in the second case, the hexagon got collapsed into a line because I only have two congruence classes connected directly. These congruence classes have a lot of nice properties. So if you take anything that's, so for example here, A, B, and D are all lower than C, E, and F. So we can define something, we can define an order in the congruence classes that the congruence class of A, B, and D is lower than the congruence class of C, E, and F. So I can also work with, so my resulting poset is also a lattice actually, and also has meets and also has joins. Here are some examples for, because what we find is that if you contract certain edges here represented in red, well, this phenomenon of preserving meets and joins propagates throughout the whole lattice. So for example, here, if I contract the edge on the left, this one gets contracted first, and this one in this hexagon induces all of these other contractions. This one contracts this one to the side in this little square. This blue one right here contracts nothing in this hexagon. And you get the idea. You contract a few little ones, and just by asking the congruence to preserve meets and joins, it propagates all throughout the whole lattice. And that can be an issue computationally, and I'll refer to that again later. So one particular thing for what I'm going to talk about is that we will not be considering all possible lattice congruences. We will be only taking the ones that start by contracting none, one, or several of the edges that are here in red. And these are the ones that I'm mostly considered on. And you can take congruence of other edges as well, but those don't define the things that we want to study, that is Permutree in our case. So we do not know much about them, and I won't be talking about them at all here. So with that in mind, now that we got everything, well, let me start telling you about how to go from everything that we talked about up to automata. So the main idea is that, okay, we have lattice congruences, but lattices can get really messy really fast. So we want something more simple to study them with. And in our case, we found out that, well, since we are actually only interested in these red edges are basically codified by the Coxeter graph of permutations. And in this case, the Coxeter graph for permutations is just a straight line with n-1 nodes. And how is this codification actually codify things in contractions in the weak order? Well, if you consider the nodes 1 and 2 of the Coxeter graph, what this line represents is basically the braid relationship between S1 and S2, and that is that S1 times S2 to the power of 3, that is the identity. And that relationship is what is codified by the left hexagon in my picture. And similarly, if you do it with 2 and 3, you get the right hexagon, and they are connected by the transposition S2. And at the bottom is the identity. So if I want to codify the contraction that I'm making, well, I'm either contracting the left side or the right side of the hexagon. So I can go to the graph and say, okay, I'm orienting an edge to the right from 1 to 2, or to the left from 2 to 1. So in this case, I contracted the right side, I directed in that way, and I'm done. That projection is fairly simple, but the nice thing is that with this we actually get orientations of the Coxeter graph, and these orientations are special because you can have a graph that has no orientations, only one orientation, a complete orientation, or a graph in which some of the edges can have several orientations at the same time. So say if I contracted both sides of the hexagon generated by S2 and S3, that would amount to orienting the edge from 2 to 3 and from 3 to 2 at the same time. And just as a note, the work of Coxeter is actually phrased in this way, but he only does it for complete simple orientations of the Coxeter graph. And by complete, I mean that everything is oriented, but by simple, I mean that everything's oriented with only one orientation. So no multiple orientations and no partial orientations. So our work will basically consider all of these cases at the same time. And well, a bit of a half step here is that I can make this simpler because I can just create 2 sets to encode all of these orientations, because I know that it's just a simple line. So I can define 2 sets, U and D, such that J is in U. If in my Coxeter graph, I have the edge between J minus 1 and J oriented from J to J minus 1, or I say that J is in D if the edge is oriented from G minus 1 to J. And in this case, well, yeah, the orientation may be this, the orientations may give us disjoint or overlapping U and D, and also partitions of a certain set. But the important thing is that this set will always be 2 up till n minus 1. Nothing else in between. We won't consider n or 1, and they'll be important later on as well. And finally, how do we define our automata from this? Well, it's all based down onto the braid relationship once again. So if I have an edge going between J minus 1 up to J, I'm going to define this following automata recursively once again. And this is the definition of the automata right here. And it's being done in a recursive fashion. So here's an example of what's the complete automata. So here, let me take a second and redefine what an automaton is. So we are interested in working with the reduced words of a certain permutation. And automatas read words. So automatons are based on nodes, which are the circles here, which can be accepting or rejecting nodes. And on top of the nodes, they also have transitions, that go from one node to the other. And in this case, our automatons will read reduced words of the automaton. So that's really important. All of the words that we will be feeding our automatons will always be reduced. So say, for example, that I have the word SJ, SJ plus one, SJ. In that case, I start at the starting node and I read, okay, I have SJ, I go to the next node, I have SJ plus one, I get here, and I read SJ. So in this case, not all of the transitions are explicitly drawn, because that would be really complicated, because there are a lot of loops, because everything that's not drawn is a loop. So SJ, for example, here is a loop. So I have SJ, SJ plus one, I read SJ as well, I do a loop here. But if then I did SJ plus one, SJ plus one, how would I do it? Well, I go to start, I do SJ plus one, I do SJ plus one, and I ended up in the same node, and that's not a coincidence. That's something that I will show you later. But if instead I took, say for example, SJ minus one, SJ, I start SJ minus one, SJ, and this word is actually rejected by the automata, and the phenomenon that will describe why certain words are rejected and why certain reduced words are accepted will basically be what we are interested on later. So the last thing that I would like to say about these automatons is that they actually codify how and which permutations are sortable for our algorithms, and they codified in the following way. If a permutation has a reduced word that ends up in the first row of nodes, these are the healthy nodes, and this represents that my permutation is as far as it can from not being sortable. So we kind of treat it like sort of a disease, not being sortable. So in that way, with that idea in mind, we say that the first row of nodes are healthy nodes. The second row of nodes are ill nodes. And the third row of nodes are dead nodes. So everything that gets here is rejected, is dead, and everything that ends up in the second row is ill. So it's basically saying that if something gets here, it's almost not stack sortable, but it tried the best it could. And I'll explain more of that in detail later. But here's an example with S5 and J equals to 2. And I thought that this would be like a good point to make an example before going more deeply. Okay, so yeah, until now I just gave you an example of like the construction, but before the actual example with permutations that Mantel is waiting for, I'm going to tell you like the main theorem that we found and why are these automata useful. And that is that being accepted or rejected by our automata actually is equivalent for a permutation avoiding or containing a certain pattern. And in this case, it's important to note that when we mention a pattern like JKI, as in the theorem, J is fixed, because in general, when you talked about, I consider 2K3, 2, 3, 1 avoiding permutations, we always consider like the relative order throughout the whole permutation. But in this case, our J is fixed. So if we say we want to avoid 2, 3, 1 permutations, that 2 is fixed always. What we care about, the relative order, is between I and K with J. So a little tiny example of this is the following. If you take the permutation 4213, this permutation avoids 2ki. You can check that directly yourself, and has several reduced expressions. But actually, it has one special reduced expression, which is given by S3, S2, S1, S2. And if we feed that to the automata, well, what does the automata read? Well, the automata starts reading from left to right and goes, okay, S3, I do a loop here. S2, I go to the right. S1, I do a loop. And S2, I go down. So I ended up in an accepting state. I'm accepted by this automata, and it's all good and dandy. We have a rejection between pattern avoidance and the notion of being accepted or rejected by a simple automata. And on top of this, the accepted reduced words by this automata have actually a really nice structure, and Nathan Reading describes a several notion of this as a search tree-like structure, and that'll be more obvious later. But some things that I would like to highlight is that, first of all, the set of accepted reduced words is closed by prefixed or by taking a prefix. So, for example, if I have the permutation S2, S1, S2, I know that is accepted here. And if I take a prefix, it's just basically taking a sub walk of the walk that I did to get here. And since my walk only traverses through accepting nodes, I know that I'll be accepted. So that's something fairly obvious, but important nonetheless. Another one of them is that all the reduced words are actually accepted at the same state. So if you have a permutation and you find randomly one reduced word that is accepted somewhere in the automata, you know that all of the other reduced expressions that are accepted by the automata will end up in the same state. And what about the ones that are not accepted? That's a bit more dicey, but I'll tell you more about that later. And finally, if you have a permutation that is accepted, that it has a reduced expression accepted by the automata, then there is actually a very special reduced expression, which here we state that it starts with its descents, and how it translates on to this automata is that it prioritizes healthy states. So that is, my permutation has a reduced word that tries to stay in the healthy states as much as it can. It's trying to not get ill or die as hard as it can until either it ends and it's healthy, or it has to get a little bit ill, or they always die. So there's always this one reduced expression. And all of these properties have actually nice consequences or corollaries, if you want to say it that way. For example, the one that all of these are accepted in the same state can be trickled down, actually. And you can prove that easily, just showing that if you do a braid relation or a community relation between two reduced words, they don't change state. But actually, we can do one better, and that is the following proposition here. And that is that all of the reduced expressions of a permutation and at the same healthy state of the automaton if there's no inversion between J and something lower than J. So I have no permutation of type of the kind 1J, 2J, 3J, 4J, and so on. If instead, no. The second case is that all of the reduced expressions end at the same state, and that is, it can be healthy, it can be ill, or it can be a dead state. If all of if the relative order between J and anything bigger than it is in the normal way. That is that I don't have any transpositions between J and J plus 1, between J and J plus 2, or J plus and N. All of those tuples are in the same order. They are not transposed anywhere. But if I have some inversions with J, so say that 1 got transposed with J, or something bigger than J got transposed with J as well, we have that the reduced expressions that are accepted will end up at the same ill state. So we can assure you that they are all in the same state, but none of them will be healthy. If you have both of these types of inversions, your permutation will be ill in the best of cases. And now, finally, let me give you some examples. And first of all, the structure that flourishes from these properties that I just mentioned is actually a tree, a tree within the weak order. And if you see it here, everything that's colored blue are accepted permutations by this Permutree algorithm, and the edges that are colored actually show you which is the reduced word that is accepted precisely by the automata. And so, and to go and do the examples, before that, I need to tell you what the algorithm is actually. How do I take a permutation and how it's sorted by the algorithm for us to define something that is sortable or not with these automatas. And that will basically have as its nucleus this property that there is this special reduced expression prioritizing descents. And our algorithm is basically the following. It's this, but this is an ugly slide. You don't need to read it completely. The important thing is that this first part of the algorithm is what's saying I need to stay alive as much as it can. And that translates into permutations that I need to do as many descents as I can. But if I'm obligated to do something that's not a descent, then I'm starting to get ill slowly and progressively. And here's an example of how this happens, how this works, and how this basically gives you a reduced word, a candidate reduced word. Yes, because practically, if you're going to compute things, you don't want to compute all of the reduced words of a permutation and try one each time to see if my permutation is accepted or not by the algorithm. You want to have a good candidate that's going to give you the most chances to be accepted or not by the automata. And this is what this algorithm is. So you just give me any permutation, and you happen to have given me the permutation 3, 4, 2, 1. And you're asking me, okay, give me a reduced word that best approximates the fact that this permutation is sortable or not. And I say, okay, I start with it, and I start seeing the descents of this permutation. And I start going from left to right, starting from 2, which is the j that corresponds to automata, and I check, okay, is there a descent between 2 and is there a descent between 2 and 1? No, 2 and 3. Yes, there is. So I multiply my permutation on the left by this position S2, and that changes the values, the position of the values 2 and 3. And my candidate reduced word, I start constructing it by multiplying the same transposition to the right, and I get this 2 here. Then I check again, now with j equals to 3. Is there a descent between with L equals to 1, I meant. Yeah, is there a descent between 2 and 1? Is there an inversion between 2 and 1? Yes, there is. I change the values here and I multiply on the right for my candidate reduced word. And I keep on checking each time for descents in an appropriate manner. And if my algorithm ends up at the identity, from what I said before, that should mean that this permutation is sortable. And come and behold, this reduced expression that we find at the end is actually the reduced word for 3, 4 to 1. And you can go to the weak order, you can follow this path, and yes, in fact, you do get the permutation that you start with. If instead you try this with a permutation that is not sortable, you do the same thing. You check for descents. At the end, you end up with a permutation that is not the identity, and that with our theorem, that means that it does contain the pattern 2, 3, 1 that is clear here, and the reduced expression that we end up with is basically one that tried its hardest to get to our permutation, but it didn't make it. And that's just another way of codifying that this permutation is not sortable for this algorithm.
Hey, Daniel, I have a question. Can you
Yes.
go over what the L was again? I'm not understanding where you're, like, how you're choosing the L in this case.
Okay,
Because
so
sometimes it looks like you're going from like 1 to like in numerical order, but in this other example, you went from 3 to 2. So I don't know, like, I can't figure that. I don't remember that.
yes, so there's something important here, and that is that actually this is based on a total order that I gave to the transpositions from S1 to S3. I gave a total order to them, and that's how I want to try the descents. So in this case, I start with the L. With the L is the one that's telling me which descents to check. So L equals to 2 tells me to check the descents between 3 and 2. 1 tells me to check the descent between 2 and 1. And between these cases, depending on my permutation, I change the J as well. And that's basically that's what's happening here. But
yeah, so like, for example, if in the first row, you have L is equal to 2, right? But you could also theoretically have L equals to 1, right? Because 1 and 2 also have a descent. So why L equals 2 and not L equals 1?
So again, that's the total order that I take, but
okay,
that's like
I'll have to look at the algorithm
details
later,
that I have.
Don't worry. Okay, that works.
Okay, so yeah, so that's an example that is not, that's a non-example. And well, all of this that I have been doing corresponds, if you go way back to the beginning of my presentation, to taking a simple orientation of my graph. So I basically have the whole graph and a single orientation. But I said that we can have multiple orientations. We can have a complete orientation of the whole graph, or edges that have multiple orientations. So what's up with that? What happens when I take multiple orientations? And well, if I have several orientations, what I do is something called an intersection of automata. And simply put, an intersection of automata is just an automata where the nodes are pair of nodes, and the connections between the nodes are pair of connections. So for example, here is a simplified version of the intersection between these two automata. This starting graph represents the starting graph of both of them. If I take the transposition S3, in this one I go to the right, but in this one I stay in the same node. So in the intersection, it translates to staying in the same node if you see it from the second automata, but in the first automata you move one. So you can think of it as copying several copies of one automata within the other. So if you take the intersection, you have actually 25 nodes, but the simplification only has 8. And in the intersection, the arrows that are in blue correspond to arrows that don't change the state of the first automata, but do change the one of the second automata. The reds are the other way around, and the twos and the orange ones are the ones that change the node of both automatas. And in this case, I say that a node in the first row is healthy if all of I say that a node in the intersection is healthy if all of the nodes in the intersection are healthy. It's ill if one of the ones in the intersection is ill, if any one of them is ill, and it's dead if one of the nodes that I took the intersection from is dead. And with intersection of the automata, we can do the same thing. We can feed it reduced words. You can see what it gives, what permutations it accepts, which one it rejects. And once again, the structure that it gives is this one of a tree inside of the weak order. And this is interesting if you intersect more automatons, it just trickles it down. It never gives something that is disconnected. It will always be connected, and it will always codify avoiding more patterns. So if I take intersection of two automatas, this one encodes avoiding one pattern, and this one encodes avoiding another pattern. The intersection will encode avoiding both patterns at the same time. And this is a second version of our algorithm with some more nuances, some more details that are technical, but the general idea is the same here. The first part, the first if, is just try to stay healthy as much as it can, try to check for inversions based on the sets and these else and the total order of the transpositions. But if you fail to do that, if you can't do that, if you have to get ill, then you do this thing that's here in the bottom, and maybe you stayed healthy in some of the automata, but in one of them you had to get ill, and that's all of what this is codifying behind curtains. And once again, here it's a bit more complicated because I have several sets, and I need to define a new variable k, but the idea is still the same. You give me a permutation, I start checking for descents in a certain order, and if I can check for these descents, I check for the descents in this way. If at the end I end with the identity, our permutation is Permutree sortable for this algorithm, and if not, it's not. And the reduced word that you get at the end is the best that you can get. So in this case, it's 3214. it amounts to avoiding two types of patterns here, and it avoids it. It's Permutree sortable for this algorithm, and it gives S1, S2, S1 instead of the other one. So since I'm running out a bit of time, let me close up with what C-sorting has to do here. What is this, and what's the deal with other Coxeter groups? So C-sorting, or also known as Coxeter sorting, was something I'm 80% sure made by Reading in his paper as well. And it's the following. I will define it with an example because it's kind of complicated to say directly. So say that you have the permutation 3, 4, 2, 1, and you take a Coxeter element. That is a multiplication of all of these simple transpositions. So that is, just take all the simple transpositions, permute them in a certain way, and take the product of that. In this case, we're going to take S2, S1, S3. And you're going to consider the infinite word, and that's just copies of the Coxeter element, one following the other. This has finite length, infinite type, but we're going to say that it's infinite for simplicity's sake. And we have several copies of the Coxeter element, one in red, one in blue, and one in brown. And with this in mind, we're going to define a special reduced expression for our permutation. And that's going to be the lexicographically first reduced expression inside of C infinite. That one is going to be called the C-sorting word for this permutation. So this depends on C as a permutation, but not C as a reduced word. And that means that you can change you can do commutations in your Coxeter element. That's not going to change what we're going to say afterwards. But if you change your Coxeter element, of course it will. So in this case, for our permutation, the C-sorting word is S1, S2, S3, S2, S3. And last but not least, I will say that my permutation is C-sortable if the position in which these components of my C-sorting word achieve a certain structure, and that is that the support of the first part contains the support of the blue part, contains the support of the brown part, and so on and so forth. So basically, I have a nested notion between of the transpositions that form my word inside the infinite word of the Coxeter element C. So to land this definition a bit, let's check our example. Is this permutation C-sortable or not? Well, I start checking everything. So S2, S1, S3, that's the complete support. S2, S3 is just one part of the support, but with a hole here, but I don't have anything else here. So this permutation is C-sortable, nice and easy. But if I took this, the same one, and I multiplied it by S1, and it had this brown part of this S1, then it wouldn't be C-sortable because this middle part doesn't appear in the blue part. So this nested containment of the supports is not happening, does not happen. And in that case, it wouldn't be C-sortable. So this is just another algorithm that takes permutations and rearranges them in some way that I'm not presented here, but so we can define things that are sortable or not. And the other main theorem that we have is something that wraps up everything, including this C-sortable sense. And it's the following. Starting from bottom to up, with the sense of what we have been doing in this talk, we have that your permutation avoiding a certain pattern, j ki if j is in U, or kij if j is in D, is equivalent for having a reduced expression accepted by each of these automatas corresponding to each of its j's. This is equivalent for there existing a reduced expression actually accepted by all of these automatas at the same time. This in turn is equivalent for the C-sorting word precisely being the one accepted by all these automatons at the same time. And this is all equivalent to pi being C-sortable. So basically what this theorem is saying in the end is that the C-sorting word defined by reading is actually the word that you want to try with our automatas. It's the word, is the best chance that your permutation is going to have of having a reduced word accepted by these automatas. So that's pretty nice, because C-sortable words and sortable and Coxeter elements have a ton of other connections in mathematics that I'm not going to get into, but it's just another nice thing that we have found. And well, in this case, as I have been saying Coxeter and Coxeter again, especially with this part of Coxeter sorting, it's only natural to think about other Coxeter groups. And that's what we have been working on as of now with Vincent and Vivian. And what we have found is that this is in fact generalizable to type B using the same notions of orienting the Coxeter diagram and reading automatas from it. It sort of works in other Coxeter groups like type D and H. We have been working especially with type D and B because those have permutations that encode them, signed permutations. But things start to happen, weird things start to happen in type D because there is a fork in the Coxeter diagram, and in type H, we think that it's because of the root side of the problem, but we're not too sure, and things are happening over there, but it does seem to work. But the other important thing that doesn't have to do much with the combinatorics, but with the computations, is that checking this algorithm in SageMath actually gives you a faster way of determining, not of doing lattice congruences, but of getting minimal elements of lattice congruences for the recorder. So the main example that encouraged me to say this out loud is because if we did a simple lattice congruence for type D6, it would take close to 3 hours or 2 hours and a half in average for it to be done. Meanwhile, if we did our code and we checked for these properties, it would only take like 6 minutes, I think, or 2 minutes, something close to that. So, but there's a caveat, and that is that we're not recovering the whole information of the lattice congruence. We're only recovering the minimal elements, but even still, it's still better than just calculating one contraction of an edge and everything that it's spanned within the recorder because of it. So that's everything that I wanted to talk about, and here are some references of all of this. Thank you.
Awesome. Thank you very much, Daniel. Let's thank the speaker.
I love the soundtrack.
Are there any questions? PS for people, it's already after 4, so if you need to go, feel free to go just in case you have meetings and stuff. But if not, feel free to ask any questions.
I think by now I'm okay. It's
Uh,
good. It was a very clear talk. Thank you.
I do have one question. So all of this is done for the minimal elements in your intervals. Is there
Yes.
hopes for being able to grab the top elements in your intervals?
Yes. So let me think. I don't want to say anything that's wrong. So I haven't thought of it in terms of contracting edges, but if I recall correctly, like you can dualize. Oh, you can invert the whole poset, and in the case for the recorder, we know that it's the same. And if you take the opposite contractions from the ones that you did before, so say if I have a hexagon, I contracted the right edge, I flip it and I do the one on the right.
So you have to look at the dual poset
to get
basically.
the minimum. Yes. You can
Okay.
get the minimals of the dual, and those
Okay.
correspond to the other ones.
So there's no like direct way. You have to go into the dual in order to calculate it.
Yes, as far as I know, no.
Okay.
You have to go to the dual.
How about for infinite? Like, have you looked at infinite ways of doing this or not yet? Or not at all?
That's the next stage we hope after we're done with finite types.
Okay.
But it's still kind of a mess because, well, at least in this case, the good thing is that these algorithms kind of go from top to bottom. Start with the permutation, so you don't really need the fact that that your poset has a top, as in contrast with the coding Sage at least, or some of the elements of Nathan Reading. But well, Reading also has several papers of doing this same in the general case, in the infinite case. So maybe, but that is just some inner forms between with the root perspective. So maybe there are things, probably there are, but it's pretty far in the future for now.
All right. I have more questions, but I can ask them at another time because it's already 4:10. Are there any other questions? Okay, seeing none, let's thank the speaker again.